audio of what anything I'm saying. Um, is that Harsha?
Yeah, hi.
Hi, how are you?
I am good. I'm good.
So I was just about to start going through this algorithm that you guys started learning about on Tuesday from Priyank. And so one of the first things just I wanted to highlight is the fact that in homework 5, you're asked to implement this algorithm yourselves. And so if you look at homework 5, basically I provide, you're supposed to read in a covering problem and then apply this algorithm to generate a minimal cover. And one of the first things that's really important to think about when you're doing that is how do you want to represent your rows and columns in your covering table. So, whoops. So like when you're solving a covering problem, you have a table like that. And the goal is to apply rules to reduce it and eventually solve it. So the way I did it in my implementation is I made it a linked list of strings. So you have basically each string is 10 dashes, and then they're linked as a linked list. And then what you do is that when you remove like a row from this list, you are, let's see, so let me go forward. So when you remove a row from the list like that, you're basically deleting out one of those strings. And when you remove a column, that's the same as putting a dash, or it's the same actually as putting a dash in that entry. When you're putting dashes through the entire column. So you just go through a particular position through all the strings. And so this is, I mean, you can do it however you want. The challenge is that if you do it, though, as just matrices all the time, then you end up copying your matrix all the time, and it's quite inefficient. And you actually also use a lot of memory because you'd need to create a matrix to be any arbitrary size unless you resize it each time. The other thing to keep in mind is because this is a recursive algorithm, is that when you do things like you see in this algorithm where it says it calls BCP, which is calling itself, you're going to enter this recursively, and you need to make sure that you're copying in copies of A when you go in. You're copying the matrix so that when you come back out that you haven't modified your original. That's another tricky thing to keep in mind. So the next assignment, it's a 2-week assignment. Okay, so the assignment that's due on Friday is the one about graphs, and that's based upon the lectures before I left. But the next one is a 2-week assignment where you're actually implementing this algorithm. And please, please don't leave it till the last day. This is hard. This takes some time to implement this thing. So I would start working on it as soon as you can. So now that you, Harsha and Zaki, that you're here, I was going to ask, do either of you have any questions from Reduce? Was it clear from Priyank's lecture?
From the last lecture,
Yeah.
I did not attend it.
Oh, okay.
I
Then,
mean, I'll catch up with it. I'll talk to Vikas or someone and catch up with it.
all right. Zach, do you have any questions about Reduce? I can't hear you. Do you have, okay. So it was clear to you from, how was Priyank's lecture for you, Zach? Was it clear? Okay. Yeah, so how about in general? I mean, does it make sense what I said about how to implement the data structure? So the key thing, I guess, is just think about how you want to describe a matrix. So if you look at the BCP algorithm, you need 3 things. You need A, that's a two-dimensional, I mean, that's a matrix, a two-dimensional matrix. You need, or a two-dimensional vector. And then you have X, which is a one-dimensional vector. This is your current running solution. Basically, what choices you've made in the covering problem so far. And then you have B, which is the best solution you found along any path as you're going through. Now, A and X have to be copied every time so they have to be passed in as a copy each time you move through the matrix. B, on the other hand, is going to be globally true because it's the best solution you found over all branches of the tree so far. So the way the BCP algorithm works is the first step is you take this original matrix and you call the reduce algorithm, which is this algorithm that you guys learned in the last lecture that goes through and applies these rules of finding essentials, deleting dominating rows and dominated columns. And it keeps going until eventually, possibly, you've solved the matrix. So if the reduce algorithm reduces the matrix down so that there's nothing left, what you'll have is A will be empty, so you'll end up with basically no matrix, and then X will have your solution in it, which will have zeros, ones, and dashes. And anything that's a dash, you'll immediately turn into a zero because those would go into your cost if you didn't turn them into zero. So it's better to just make anything that's a dash into a zero. And then you're all done. You found a solution. But that's not always going to be the case. Sometimes there is no solution found after reduce. Sometimes you can get yourself thinking reduce is really powerful, it worked, but there are matrices that are cyclic. Did he mention cyclic yet? I don't think so. So there are matrices that have a cyclic core.
He did explain what a cyclic matrix is with an example.
Okay, good. So a cyclic matrix essentially is a core that basically no reduce rules apply anymore. Okay, so then the next line of the algorithm is computing a lower bound. Now the reason why you need a lower bound is it's going to tell you, starting from here, what's the best solution I could possibly find. So the way to think about your search tree is it's a tree, so it's basically, at this point, after you have hit the cyclic core, you need to try each variable assigning it a 0 or a 1. So you assign it a 0 and say, what's the best I can do if this variable is 0? And then you take the other choice, what if the best solution I could find if I assigned this to 1? But the problem is that if you could just sort of try all possibilities. But if you do that, and let's say that there's n variables you haven't assigned yet, you're going to have 2 to the n possible assignments that you're going to make for those n variables. So it'd be very expensive to solve BCP if that's what you had to do exhaustively. So in order to avoid going down and assigning every possible assignment to these variables, what you're going to do instead is you're going to calculate what's the best I could do starting from here. What's the smallest solution I could get starting from whatever reduced matrix I have. And that's what the goal of lower bound is for. And then, Harsha, have you seen covering problems before?
Yeah, I have seen them before.
Okay, so stop me if you have questions, because I know that you didn't see the lecture exactly, but basically you're trying to find a minimum cost cover, like minimum number of prime implicants to cover all minterms, for example.
Yeah, I'll stop if I have any questions.
Okay, great. So then basically then what you do now is once you calculate the lower bound, you check to see if the lower bound is greater than or equal to the cost of the best solution. Because if the lower bound is greater or equal to the cost of the best solution, there's no reason to continue down this subtree. You've already found another solution that was equal or better in cost. And so that gets returned and you just terminate, right? You terminate this branch of the tree, of the search tree. If that's not the case, then you next have to check to see if this is a terminal case A. So terminal case, there's two types of terminal cases. One type of terminal case is where you've actually solved A, meaning A is empty, it has no rows left. And in that case, you've solved it, and if it has no rows, then you can just return the solution you have because it is a valid solution. If on the other hand, it doesn't have any rows, on the other hand, it still has rows, but it's a terminal case, this is an infeasible case, meaning there exists no solution down this path. And so in that case, what you do is you return the best that you found so far because you can't actually generate another solution down this path. Does that make sense? Is that you, Ji-Chen? I just saw another person join. Is that you, Ji-Chen? Or some, who just joined? Or is that Hawaii? I see a white board of some sort.
No, it's G-Chan.
Okay, hi, Juchen. I was just working on, were you at the lecture on Tuesday from Priyank? Okay, he's muted. All right, I'll just carry on. So then if, on the other hand, it's not, the lower bound is less than the, could be better than the best you found so far, and it's not a terminal case, the next thing you need to do is start going down this tree. So you're basically searching this search tree, right? So you're going to pick a column and make an assignment. So then you call a function called choose column, and what it does is it tries to guess what's the best choice to make right now. So it's going to heuristically decide what's going to be the best variable to branch on. So you pick a column, and then what you do is you set that variable to 1. Basically, you're saying, I'm going to include this in my solution. And then what you do is if you've set it to 1, you're going to select that column in the matrix to reduce it, and then you're going to call the algorithm recursively and see if you can basically jump in the algorithm and start applying reduce and going down the rest of the search tree. Then when that returns, you get back this solution, which is the solution if you pick column C to be 1. And if the cost of that solution is less than the best you found so far, that becomes your new best solution. And if the cost is equal to the lower bound in other words, that you hit your lower bound exactly, then you can return this. There's no reason to look at the situation where you set it to 0. So if it's not better or it's not equal to lower bound, you're going to go to the next case and you're going to set it to be equal to 0, and then you're going to remove the column, and then you're going to recursively call the algorithm again. Okay, and then if the cost is less than the best, then once again this becomes your best, and then when you're all done, you return the best that you found down this path. So basically, this is how the algorithm gets recursive: is you hit a cyclic core. You pick a column and you let's try it to be 1, let's try it to be 0, and then let's solve and repeat going down. So let's see an example of this. So if it's solved, then the cost of the solution is based, so when you're doing this bounding, if A is empty, meaning it's solved, then the cost is just simply determined by equation 1, and equation 1 was back here. Here. So the cost is basically you take the minimum, you basically take and sum over all of the weights. So whenever a variable is 1, then you add on the weight of that, and that becomes the cost of the solution that you found. And then what you do is, but then if it's not solved, that means that your matrix has a cyclic core. And if it has a cyclic core, we have to test whether or not a good solution can be derived from this partial solution starting from here. And the way you do that is you determine a lower bound L on the final cost, starting with the current partial solution. And if L is greater than or equal to the cost of the best solution found, you're not going to find any better solution down this subtree. So finding the exact lower bound, though, is as difficult as solving the initial covering problem. So this is what we were talking about at the beginning when you asked me this question, Vikas, is that if you could actually know the real lower bound, you really would have to know what the solution is going to be. So there's no way to know exactly what's the best you can do down this subtree. So instead, there are many heuristics that have been developed, and I'm going to introduce one called maximal independent set. And this heuristic, basically what you try to do is you try to figure out what's the minimum number of columns I'm going to need to set to 1 that are going to be solving disjoint parts of the remaining subproblem. So 2 rows are independent when it's not possible to satisfy both by setting a single variable to 1. And any row which contains a complement variable is assumed to be dependent on any other clause, so we must ignore those rows. So here's the algorithm for maximal independent set. So what you do is you start with an independent set, which is empty set. We delete all rows with complemented variables. You then choose the shortest row, and the shortest row is the one that has the smallest number of 1s in it. And you add that row to your independent set. And then you delete all intersecting rows from A, and you repeat this until A is empty. And then your lower bound is the size of your independent set plus the cost of the subsolution that you found so far. So here's an example. Okay, so this matrix is cyclic. If you take this matrix and you try to apply the reduce algorithm to it, what you're going to find is that there's no rules that apply. There's no essentials. There's no rows that are dominated, no columns that are dominated. So there's nothing you can do to this matrix to make it any smaller. Is this clear? So yeah, so as an exercise to the reader, if you look at this matrix, take all the rules that you learned from pre-inc, see if you can apply any of them. The answer should be no. There's nothing you can do to this one. And so at this point, there's no fancy reduced rule we can make this matrix any smaller. So the question is, how do I proceed? And the way you proceed is in this branch and bound fashion. But before we proceed, we want to know what's a guess as to what's the smallest number of these columns I'm going to need to pick, set to 1, in order to solve this matrix. So the bounding, so to calculate this bound, we use this algorithm. There aren't any complemented variables. There's no 0, so I don't have to delete any entries from the row. So what I want to do is pick one of the shortest rows. So for example, row 1 is one of the shortest rows because you have rows with 2 1s in it, or like row 5, which has 3 1s. So you want to pick one of the rows that has the shortest number of 1s, like this row 1. And now what you see is, well, row 1 intersects with row 2, because if you solve row 1, you might solve row 2. Because if it happens to be that you solved row 1 by picking x1, you'll have solved row 1 and row 2. And if you solved row 1 by picking x2, you'll solve row 1, you'll solve row 7, and you solve row 10. So you know that when you solve row 1, you might have solved rows 2, 7, and 10. So remove row 1, 2, 7, and 10 because the solving of this row 1 might have solved the others. You don't know that it did because you don't know whether you chose x1 or x2, but you're conservative about it and say it might have solved these other rows. So we think it's possible that choosing one solution might solve all those other rows. Does this make sense? Can I get verbal acknowledgments? I feel like I'm talking to the wall.
Yes, it does.
Okay.
Yeah.
Thanks. So now I have to pick the next shortest row. So that's like row 3, for example. So if I pick row 3, to solve row 3, I either have to set x4 or x5 to 1. And if I set x4 to 1, it's going to solve 3, 4, 8, and 9. And if I select x5, it's going to solve 3 and 5. So I'm going to remove 3, 4, 5, 8, and 9. And that leaves me just with row 6. Now row 6 could not have been, solving row 1 and solving row 3 would never solve row 6 because they don't overlap in any column entries. So row 6 has to also be added to that maximal independent set. So what this tells me is that at a minimum, to solve this, I'm going to have to choose at least 3 columns to be 1. And you have to be very careful when you do bounding. If there existed a solution with 2, I'm going to now miss it. So you have to say, you have to be very conservative like we were here to not let this set get any smaller than it really could be. There literally is going to be no way to solve this with less than 3 columns being chosen because of the way that we defined these intersections. So there might be a solution, there might not be a solution that has 3. This might not be solvable by 3. So the lower bound must be strictly lower than any actual real solution. So any algorithm you come up with bounding has to guarantee that property. Does that make sense?
Yes, it does.
So this is critical because if you bound early, you're going to miss solutions and the algorithm won't be optimal anymore. Okay, so now we've just finished line 2 of the algorithm. We calculated the lower bound on your matrix. And encourage you guys to ask questions. You're going to implement this algorithm. So if any of this is in doubt, please ask questions. And if you're Microphone's not working, Zach. You can type questions. So then now we've computed the lower bound. Implementing cost is simply what you do is you just go through and count how many ones you have. Actually, so one key thing is in your homework, you're going to do a non-weighted. All your weights are going to be equal to 1. But in general, the solutions can be adapted to have non-equal weights across the columns. So then if your lower bound is greater than or equal to your cost of the best you found so far, you're done. You don't need to go down this subtree. Okay, so the next line of the code is checking terminal case. So the way you check for termination, this tends to be one of the trickiest things, I think, when people implement this. So the easy case, if A has no rows left, so basically reduce has reduced out all the rows at this point, then all the constraints have been satisfied by X, and this is a terminal case. Basically, you found a solution. There's no more reduction that's necessary. However, there's another terminal case, which is no solution exists at all. So here's an example of, and if you just look at this Boolean formula for a second, you can see that there's no assignment to x1 and x2 that'll make this Boolean formula true. Right? So if you set x1 to 1 and x2 to 1, you can solve the first clause, but then all the other clauses are going to be false. And no matter what choice you make for x1 and x2, you can't make this formula be true. Okay? So if you map that formula into a covering problem like you see down below, you have 1s for those first two clauses, a 0, 1 for the next two, 1, 0, and then 0, 0 for the third clause. So when you look at this and you say, okay, can I solve this? You'll realize that you can't solve it because you have a situation where the only way you can solve one of these clauses is by making a choice that's going to make the other clause insolvable. So what you could do is, so if you select x1, for example, when you select x1 to be 1, you're going to solve row 1 and you're going to solve row 3, but you're going to be left with 2 and 4. One of them is going to have a 1 in it and the other is going to have a 0. So row 2 will tell you that you need to include x2, and row 4 will tell you that you need to exclude x2. So you have an essential, which is both an essential 1 and an essential 0. And so there's no way to solve it because you can't both select and not select a variable. Does that make sense? So the way this usually occurs, or the way it occurred in my implementation, is you end up with a row with no 1s and 0s in it. You start selecting 1s and 0s, selecting them until eventually you end up with a row that you can't get rid of because there's nothing left to choose. So if I check, for example, if I'm branching, I pick x1 to be 1, and then I decide to pick x2 to be 1, I'm going to be left with row 4 with a dash in it because there's going to be no choices left, with only dashes in it, because there'll be no choices left that I can pick to solve that one. So in your algorithm, make sure you think about sort of the terminal cases, and as I said, if you ever get to a situation where you have a row that has no choices left for you to pick, then you can't proceed at that point, and that's a terminal case as well. And so you need to backtrack. So in that case, A is going to still have rows left, and you're going to return the best you found so far because you can't actually find any solutions down this subtree. Is that clear? So one thing you might want to do is just to make sure your thing's working is put in like this case and make sure it comes back with no solution. Okay, so now the next step is we have to decide which column to branch on. So if A is not terminal, then the matrix is a cyclic core. And to find the minimal solution, we have to determine a column to branch on. So we're basically going to try to choose the column and exclude the column. So we're going to try to choose one solution, choose one column to include, and then see if you don't include. So it's kind of like a binary search at this point. Both try it and don't try it. So the idea of branching, so by implementing choose column efficiently, you can find good solutions faster. Because once you find the best solution that there is to be found, you should then, through bounding, avoid searching more parts of the subtree. So you want this branching to be as efficient as possible. So a column intersecting short rows is preferred for branching because a column that intersects short rows is one that's solving problems that are hard to solve. They have a small number of choices that will solve them. So to do this, we assign a weight to each row that's the inverse of the row length, where that's the number of ones in the row. And we sum the weights of the columns covered by that column, and then we choose the column with the highest value for case splitting. Okay, so let's go back to this example. So now what we want to do is we want to pick one of these 9 variables as our branching column. And so we want to pick one that's going to potentially solve hard to solve rows. So what we do is we assign a length as the reciprocal of the number of ones. So there's 2 ones, so this length, we give it a weight of 1/2, 1/2, 1/2, 1/2, 1/3, because this solves 3. And so the higher the weight, the better in terms of it being useful. So we want we want to select a column that intersects rows with small numbers of choices. So basically, all you're doing is counting up how many ones and taking 1 over that to get the row weight. And then to calculate the column weight, what we do is we add up the row weight. So column x1 is solving rows 1 and 2, which have a row weight of 1/2 and 1/2, so it gets a value of 1. x2 solves row 1, 7, and 10, so it gets a value of 1.3 or 1.33. But the best one turns out to be x4, because x4 solves row 3, 4, 8, and 9, which are all weighted with 1/2, so that equals 2. And so it looks like x4 is going to be our best choice. It's going to solve a big chunk of our problem for us. So do you guys see how this might be useful? It's only a heuristic. It's no guarantee that you're choosing the right column. But what it's doing is it's giving you insight into a column that might solve more of the problem than a different column. So both bounding and branching are, actually, if you read papers about the BCP algorithm, the key difference from one paper to another is how they do branching and how they do bounding. So there's a lot of different algorithms, a lot of different people have tried different techniques for branching and bounding to try to make more efficient solutions. Okay, so then the way you do branching is you're going to reduce the matrix by adding that variable into the solution, and then you're going to recursively call BCP on the reduced matrix, and then you're going to compute a result for setting that column to 1. If that's better than the best, you record it. If it meets the lower bound, then you found a minimal solution, so this is good. You don't need to look at the opposite case. If not, then we try removing XC. So you're going to include XC in the solution and remove XC in the solution and try to figure out which is going to be better. So that brings us to this last part of the algorithm, which is actually this adding and removing this column that you selected. So as I said before, after the choose column, yeah, go ahead.
Quick question.
Please.
So again, to summarize, so once we have reduced, so the way you set a lower bound is by selecting the rows with minimum number of ones, then seeing which column gets covered, and that should mark your lower bound.
So I think you might be mixing bounding and branching. Are you? I mean, you went back to bounding, so you're asking. This is the branching step we're going through now. Bounding was this maximal independent set. So the lower bound is computed by finding your maximal independent set, like we did here. And that tells you what's the minimum number of columns you can select. Branching is you actually select one, and you're then going to try to see what happens when I select it. Right? So if I just gave you a covering problem, the brute force way of solving it is to try every possible assignment to every possible variable.
Okay.
Right? If you just went through and enumerated the 2 to the n possible assignments to every variable, you would get every solution. You could calculate the best one by just taking what's the solution that has this, that solves the matrix and or solves the formula, satisfies the formula, and has minimum cost, right?
Okay.
So a brute force way, because basically what you're trying to find is a satisfying formula to this original problem you had, right? It's basically this SAT problem. And you want to find a minimum solution that's going to satisfy the formula. So the branch and bound, basically what you want to say is in the bounding step, you're trying to say, if I keep trying to solve the problem starting right from this matrix right here, what's the minimum number of columns that'll have to be set to 1 to make it solved? And that minimum is 3. But it might be 4 that actually solves it. There's no guarantee 3 will solve it.
Okay.
But 2 definitely will not solve it. There's no way to pick 2 columns that's going to solve all this matrix.
Okay.
So then the branching part, though, is now I need to pick a column as a starting point of which column am I going to try first. So in this case, it turns out that x4 is looking very promising because it's intersecting 4 rows, and those rows each are very hard to solve because they only have 2 choices each. So the score that it got was by far the highest score. So it looks like x4 looks like it might be a good solution. It might be a good variable to include in my solution. So that's what I'm doing now is I'm going to select x4. Now when you select x4 and put it in the solution, that solves row 3, 4, 8, and 9. Okay, so I put x4 in my solution. And that reduces the matrix like so. Is that clear? You remove every row that has a 1 in x4. So rows 3, 4, 8, and 9 each had a 1. And so when I set x4 equal to 1, it removes those 4 rows because they've been solved, right? Is that clear? Okay.
Yes.
So now at this point, at this point, we have column dominance, because if you look at x2 and you compare that to x8 and x9, the x2 column is dominating the x8 and x9 column, because if you select x2, you're going to solve everything that x8 and 9 does. So I can apply reduce, and I can reduce it and remove x8 and x9. In other words, set them to 0, because they're not any better than x2. Similarly, x3 column dominates x5 and x6, because x3 solves all the rows and more that x5 and x6 does. So do you guys remember column dominance from pre-Yank's lecture?
Yes. Yes.
Okay. So when I apply column dominance, I get to wipe out those 4 columns that got dominated. So x5, 6, 8, and 9, I set all those to 0. Because I've recursed in the BCP, I'm doing reduce again, right? So I'm taking this matrix and I get to apply all my reduce rules again. So by making a choice of one column, you might introduce the ability, you might break the cyclic core so that it has reductions again. So I got to remove some more things from it. And then at this point, what you notice is that, actually, what do you notice? Do you see any reductions?
Dominating row 2 on 5.
2 and 5. Yes, you can remove the dominating row, which you actually remove row 2 in that case.
And
but
in 7 and 10, you remove 7.
You can remove 7. But before dominance, remember the first thing you look for are essentials.
Oh, yeah.
Do you see any essentials?
No.
So an essential, remember, was a row that had a single 1 or a single 0 in it.
Oh, it was a row, sorry.
Yeah.
5.
Yeah, so row 5, actually the essential is named by the column. So x3 is essential because it's the only solution to row 5. And are there any other essentials, Meher, are there any other essentials?
X2.
X2 is essential because?
Row 10 only, or constraint 10 only has 1 in it.
Right. So
X2 is the only one that can solve it.
So if I select x2 and x3, what rows are left? Harsha. If I select x2 and x3, what rows are left after I do that?
Row 1, 5, 6, 7, and 10.
If I select column x2 and I select column x3, sorry, it's a trick question, but if I select both of those columns, what rows will still be unsolved?
Column x2 and x3.
I'm-
Rows. I mean, all the constraints are covered in those. Right?
That's right. It's empty. You've solved it totally. If I select x2 and I select x3, the entire thing is solved. So I'm done. And in this case, the solution had 1, 2, 3 ones in it. Its cost is equal to 3. And remember, the lower bound that I calculated earlier was 3. So we're done. Because we basically found a cost 3 solution, and we know that we can't do any better than a cost 3 solution, because that's what the lower bound was when we computed it for this thing. So we hit this line of, so we got back a cost 3 solution. This is less than our best because we didn't have a best yet. It becomes our best. This cost is equal to lower bound, so we return the solution and we're all done. Does that make sense? So branching really is kind of, it's kind of brute force, right? Because you're picking a column and you're assigning it a value somewhat arbitrarily. But the reason you can make it a little bit more efficient is if you choose wisely, right? If I randomly choose the column to start from, maybe I will choose like x8 or x9 and not get very far and find a higher cost solution. But because I was smart and I chose x4, I actually ended up on the best possible solution immediately. And I don't even need to go down any other parts of the subtree. I'm all done. But let's pretend like that didn't work out. If that didn't work out, then what we'd have to do is we also have to not only select it, we also have to decide not to select it. So now I'm doing this line down here at the bottom where I say, I'm going to set that variable now to 0. So if I set x4 to 0, then what happens is I'm just simply deleting that column. If there were any rows in this that had a 0 in it, they would get solved, but they don't. There aren't any rows that have a 0 in it. So I just delete the x4 column. I set that to 0. And then at this point, so Ji-Chen, are there any essentials?
X. Yeah. So the essential mean is that x8 and
x8 is an essential because of row 8, right? Because it's the only row 8's only solved by x8. So since x8 is essential, we have to include x8 in the solution. Are there any other essentials?
x9.
x9, yep. Any others?
No. No. X5.
x5. Any others?
X6.
x6, yep. So we have 4 essentials. When we set x4 to 0, notice we all of a sudden have 4 essentials we have to include. So Zach, if you select x5, 6, 8, and 9, which rows are still around? You can type it, Zach. Which rows still exist if I pick x5, x6, x8, and x9?
So 1.
Ji-Chen, I was asking Zach, sorry. And Zach is typing it because he's got an audio-visual problem. 1, 2, 6, and 7, correct. So 1, 2, neither one of those are solved by 5, 6, 8, or 9. And then we also have, 6. 6 is not solved by those, and 7 is not solved by those. So we end up with 1, 2, 6, and 7. Now this guy, unfortunately, is another cyclic core. There is no reductions. There's no row dominance, no column dominance, no essentials. So now we have to recurse the BCP again. And so
Sorry,
you,
Chris, you broke up on me there. Will you repeat that again?
yeah, so in this one, there are no, this is cyclic again. And so you'd have to pick another column to try to solve it. Because there isn't any row, there's no column dominance, no row dominance, no essentials. So you'd have to pick another column to try to solve it. And it turns out you're going to have to pick 2 more variables to solve it. So you could pick x2 and x3 would solve the 4 rows, or x1 and x7 would solve the 4 rows. And the rest of the BCP would find those other solutions. But what you're seeing is that if I don't allow you to pick x4, my solution size is going to be 6 instead of 3. So choosing x4 was really a good idea to include it. And that's what the choose column thing helps you do, is it tries to help you find that. So, so that concludes the BCP portion of this lecture. So you're going to have to implement the BCP. So this would be a great time to ask any questions about implementing BCP. Don't all speak at once. You're all muted, so maybe you're all yelling at the computer and I don't know it. Does this seem like a fun algorithm to implement?
Yeah.
Yeah, it's challenging. It's a challenging algorithm because it's recursive. But the algorithm itself is not fundamentally hard. It's just hard to keep track of because when you're debugging recursive algorithms, it sometimes gets confusing where you're at. So I recommend copious amounts of printing the matrix as it goes through and look at these examples. So in the course of the rest of this lecture, as you're going to see, the BCP is used over and over again by all these other algorithms that we are going to use for the asynchronous part of it. So BCP is not an algorithm for asynchronous design. It's just a general purpose useful algorithm for all kinds of things. But it turns out that solving, to do state minimization, state assignment, and logic-free, hazard-free logic minimization, they all require solving a covering problem. On the website, I also include 3 test cases, which are test cases from the lectures, but you're free to also come up with your own. So now that assignment, by the way, that assignment has a required milestone, which is in the first week, I want you to solve problem 5.1 from the book. And that problem is basically do the BCP yourself by hand on a paper problem to make sure you understand sort of the steps and how it works. So definitely take a look at that. And if you have questions, I mean, the assignment ultimately won't be due until a week after I get back, but certainly if you have questions, if you start playing around with it, I think you try to get started as soon as you can. Use whatever software language you're most familiar with and comfortable with to do the assignment. I don't care what you use as long as you tell me how to run it. Okay, so last chance for questions on this. It's all good? All right. So the last little bit I want to talk about state minimization. And so state minimization is the first of these algorithms that is going to make use of covering problems. So you remember back in chapter 1 where you had a flow table, and what you did is you said, okay, I want to merge rows together that can merge together. Right? So you'd find that some rows had don't cares in them, and you could merge the rows and get a smaller table. So why do you want a smaller flow table? Anybody? Why is a smaller flow table good? Why is less rows good?
Less constraints.
Less number of internal states to design.
Correct. Less number of state variables. Yep. Less rows make state machines simpler. Yes, but the more concrete answer is that if you have less rows, you have less states. So let's say I have 5 rows. How many state bits do I need at least to represent 5 rows?
3.
3. What if I can reduce it to 4 rows?
Then you need only 2 bits.
Exactly, you need only 2 bits. So reducing the number of rows reduces the number of state bits you need in your final solution. So the first step of asynchronous logic design in the Huffman circuit style is to minimize your flow table to reduce the number of state bits you need. So state minimization procedure has 4 steps. The first step is to identify compatible pairs of states. So you look at 2 states and you say, can I merge these 2 together? The next step is to find maximal compatibles. So maximal compatibles are larger groups. So 2 states, 2 rows, can I merge together? A maximal could be 3, 4, 5, basically any number of rows. And so you want to find a large grouping of rows that can be merged together. Now, it turns out that when you merge certain rows, you prevent other mergers from happening. So you have to then use something called prime compatibles to find actual maximal compatibles that will lead to solutions of minimal cost. And so those are a little bit more involved, but basically the idea is that some maximals are not always good. Sometimes sometimes it's more beneficial to merge less rows together because it doesn't preclude other rows from being merged. And then finally, the last step is to set up a covering problem where the prime compatibles are the solution. So these are groups of rows that can be merged. And the states are what needs to be covered. Namely, every state in your initial flow table must be included in one of the prime compatibles you select. You don't want to lose any rows in the process of merging. So this method of state minimization is developed for single input change fundamental mode. So this is where you change one input at a time. And it turns out this is exactly the same technique that's used in synchronous state minimization. How many of you have seen state minimization algorithms for synchronous state machines? Any of you? None of you? So, okay, so maybe our logic synthesis class, our logic design class is not teaching that anymore. Were you going to say something?
I solved the exact same problems in a relative time class for Ken.
Oh, okay. Great.
Yeah.
So it's probably a very similar algorithm. Okay, so far all the state minimization examples you've done in the homeworks have been very simple. I should say the one example you had was very simple. But take a look at this flow table. So it's not at all obvious from this flow table how you could combine the rows together to get a minimal flow table. Because when you start making certain choices, you can't make other choices. So looking at this flow table, you wouldn't know probably a priori that right now we have 8 rows, so we need 3 state variables. It will minimize down ultimately to 4 rows, as we'll see. Okay, so the way you do that, the way you figure out, so as I said, the first step is we need to find out which pairs of rows could potentially be merged, find compatible states. And the way we do that is using a thing called a pair chart. So a pair chart basically says, can A merge with B? Can A merge with C? Can A merge with D? So you go through each pair of entries and check to see if they can be merged. And it's symmetric, so you don't need the top half of the table. So a pair chart is like this. Can A merge with B? I don't also need to check to see, for example, can B merge with B? That's redundant. I don't need to check to see if C can merge with B because I've already checked if B can merge with C. So you can cut off the top of this pair chart. And so now what we need to do is fill this in to indicate when 2 states can merge together. So first of all, we need to decide when are 2 rows unconditionally compatible. So 2 states U and V are said to be output compatible when for each input in which both are specified, they produce the same output. 2 states U and V are unconditionally compatible when they're output compatible and they go to the exact same next states. And when 2 states U and V are unconditionally compatible, the UV entry gets marked with a twiddle sign. So what we do now is we take every pair of states. So we basically use this pair chart and we check, can I merge A with B? Can I merge A with C? Can I merge A with D? And we're going through and marking the ones that we think we can merge. So then we look at A and B and we decide, can we merge these 2 unconditionally? Well, the answer is no, because in X3, A goes to state D and B goes to state A. So they go to different next states. So A and B are not able to be unconditionally merged. And then we look at A and C. And again, the answer is no, because A and B are not the same next states. And then we look at, say, A and D. When you look at A and D, X4, we have E and B, they can't be merged. If we look at A and E, again, they have different next states. A and F, different next states in the first column. A and G, I think we found something. So A and G, you see that this one has A0, A and 0, and this is a don't care. In column X2, don't care, C1. Column X3, D0 dash, E1, E1, B0 dash, A dash, G0. Now this is a tricky one because A and G are not the same next state, but if you merge A and G, they are the same next state because A and G will now be the same state. So this is actually unconditionally compatible because A and G, if they get merged, are going to be the same next state, and therefore these are going to the same next state. And then finally, the last one is a don't care with F0. So A and G are unconditionally compatible. They can be merged without any restriction. And then A and H cannot be merged because the output here is 0, the output here is 1, so they can't be merged because they're not output compatible. Does this make sense?
Yes.
So you go through every pair this way. So then we look at like B and C. Meher, are B and C unconditionally compatible?
Yes.
Yes, they are. If you look through every single entry, they're compatible with each other. Vikas, how about B and D?
Okay. Uh, no.
No, which column blocks it?
X2.
Yep, because X2 has a D and an E, so it's blocked. The different next states. Ji-Chen, how about B and E? Can you merge B and E?
B and E, no.
Which column blocks it?
X2.
Correct. D and E are different. How about B and F, Harsha?
Same, X2 blocks it because of D and C.
Correct. So you basically go through each pair making this evaluation. Once you do that, you're going to find that there are 4 entries that are unconditionally compatible. So what that means is these can be merged without any restriction. Okay? So then the next thing you need to do is determine what 2 states are incompatible with each other. And 2 states are incompatible when they're not output compatible. So these can never be merged under any situation. So 2 states are marked with an X in this situation. So if you look at A and B, are they incompatible? Vikas?
So you said if the states are different, it is incompatible.
No, states different is okay for this one. It's just outputs have to be different. If outputs are different, you can never merge them. So do they have, basically you're looking for difference in outputs for a column.
No, the outputs are same.
Yeah, they're either same or don't care. So A and B are not incompatible. They have a chance to be merged. How about A and C, Meher? Are they is A and C? Oh, I scared her away. Oh no. Okay. That's one way to get out of answering question. Ji-Chen?
Sorry.
Oh, I thought you didn't want to answer my question.
I meant to press unmute.
Okay.
But A and C, column 3.
Column,
X.
correct. Column 3 makes them different, so they're incompatible with each other. How about A and D, Ji-Chen?
A and D is same. Output is same.
The outputs are the same, so it's not incompatible. Double negative, not incompatible. How about A and E, Harsha?
They are also not incompatible.
They're also not incompatible, right? Double negative. Okay, So when you go through the whole thing, you can see that these are the states that get marked with X. These are all the ones that are output incompatible with each other. So what's that leave? What that leaves is all the remaining ones are what are called conditionally compatible. What do we mean by conditionally compatible? So two states are conditionally compatible when there exist differences in their next state entries. This does not make them inherently not compatible. And the reason is because once you merge the states, it's possible that these differences are going to go away because you're going to merge them into the same next state. And so if the different next states get merged, they become compatible. So when two states U and V are compatible, only when states S and T are merged, then that entry is marked with the S and T in it. So if you look at A and B are not incompatible because they have the same outputs, but they're not unconditionally compatible because of X3. In X3, you have to merge A and D in order for A and B to be merged. So I have to merge apple and dog in order to map apple and boy together. Because the next states need to be the same, which only happens if those two states gets merged. So A and B are conditioned on A and D. So for A and C, we already said that they were, so let's look back here. So A and B, we've talked about, that's conditional on D, A, and D. But what about A and D? So A and D, Vikas, what is it conditioned on?
Sorry, merging E and B.
A as in apple, D as in dog.
Yeah. So it depends on merging E with B, X4.
Correct. It depends on merging E with B. If you merge E and B, you're allowed to also merge A and D. Okay? So what's the next one is A and E. So Meher, what about A and E? What are their conditions?
You have to merge A and D.
A and B, what else? There's actually more.
And A and E.
And A and E, yes, there's actually more.
And A and D.
And also A and D. There's actually 3 conditions to use this one. So only if you merge those 3 pairs do you get to merge this pair as well. Actually, A and E is a vacuous one because if you basically you're saying if I merge A and E, I'm allowed to merge A and E. So you don't actually need to include that one. Because if you merged A and E, you merged A and E. Does that make sense? So that one's redundant. What about B and D? B and D. So Ji Chen, what needs to?
So we need to merge E and D.
E and D, correct. More?
And A and B.
And A and B, correct. And then what did I just do? Sorry, we did B and D, right? So B and E. B and E, Harsha.
We need to merge D and E,
Correct.
and then we need to merge A and B
Correct.
and A and E.
And A and E. Yeah, so you get 3. So now that's what we just said. D and E, A and B, A and E. So the table you see we filled in now with all the entries that must be merged in order to merge the other 2 states. Okay? So now we've colored it with the 3 possibilities. It's the unconditional, incompatible, or conditionally compatible. But now at this point, it might be the case that we can find additional incompatibilities. So in order to merge A and B, I have to also merge A and D, which I could do. That's possible because I could merge those if I merge B and E. In order to merge A and E, I also need to merge A and B, which is possible, as is A and D. In order to merge B and D, I have to merge A and B. That's possible. D and E is also possible because it's unconditional. So that one's fine. If I want to merge B and E, I need to merge D and E. That's fine. A and B, that's fine. A and E, that's fine. C, to merge with D, I need to merge D and E. That's fine. And I need to merge A and G, and that's also possible because it's unconditional. So what I'm looking for are mergers that can never happen. So to merge C and F, I have to merge C and D. That's possible. To merge C and G, I need to merge C and D and F and G, and that F and G is possible. So this sounds very boring so far. So we'll run into a problem, I promise you. So D and G, I need to merge C and E. There's our problem right there. C and E can never be merged. It's incompatible. But in order to merge D and G, I have to merge C and E. So this one's impossible because I can never merge C and E. So this one needs to be marked as incompatible because one of its implications is never coverable, never possible. Do you see another one out of these remaining three that needs to be removed? Anybody?
E and F.
E and F, yes. E and F cannot be merged because C and E cannot be merged. So basically this final step is check each pair of conditional compatibles. If any pair of next states are known to be incompatible, then the states are also incompatible, and you can mark those with an X as well. And this is now our final pair chart that we compute. And so this final pair chart, so this is the, this is before, this is the final one. So this shows all possible pairs that could be merged, and some of them are mergeable immediately and some are conditionally mergeable. So, but the next step is what we need to do is find larger compatibles that include these. I'm trying to think, what time did we actually start here? How long has this been running? I don't recall.
I think you have like another 20 minutes because we started like 20 minutes later.
Okay, thanks. Is that all right with you guys? Anybody need to run or?
I'm good.
Ficus?
Zach had to go to class.
Okay. I'm recording anyway, so I can also post it for you to look at afterwards. Do you guys have do you guys have time to go through maximals and then call it a day?
Yeah.
Yeah.
Yep.
Okay, let's do maximals and then we'll call it a day. Okay, so maximal compatibles. So basically in maximal compatibles, what you want to do is find the larger sets of compatibles. So I want to merge 3, 4, 5 states together. So if S is compatible, then any subset of S is also compatible. So we're basically going to grow the set of compatibles to be subsets that are not contained by any other subset. So a maximal compatible is a compatible that is not a subset of any larger compatible. You can kind of think of them of like prime implicants, where remember prime implicants cover the maximal number of minterms. And then from the maximal compatibles, we can ultimately determine all of the compatibles that we might need. So there are two approaches to finding maximal compatibles. The first approach is you initialize a compatibility list. Actually, I think I'm going to demonstrate this one rather than go through this list. I think this is a bit obtuse. Okay, so we take our pair chart we derived from before, and the first step is we initialize a compatibility list with compatible pairs in the rightmost column of a pair having a chart having at least one non-Xed entry. So we start off with we go to the furthest right, and we see that F and G are potentially compatible. And so our first set of compatibles is FG. And we want to grow from there. The next step is we start moving from right to left, examining the columns. And we're going to start with column E, because that's the first column that has entries in it that we haven't dealt with yet. And in state E, E is compatible with H. So this is saying in the column E, what are all the things E is compatible with? It's compatible with H. Basically, any column that doesn't have an X in it. The states, these things that are listed here, are irrelevant for finding maximal compatibles. It's either X or not X. Then what we do is we intersect this with each member of the compatible set, And we're going to add any of these entries that get found merged with the column that you're searching on. H doesn't intersect with FG, so that doesn't add any new entries. We then add pairs which consist of I and any members of SI that did not appear in any intersection. So since H was never used, we're going to add EH to our set. So now our set is FG and EH. So FG is one compatible and EH is another compatible. So far this hasn't been very interesting. So now we move on to column D. In column D, we have E and H. So E and H are both compatible with D. And then we intersect EH with FG, that gives you nothing. There's an empty set. EH intersect with EH gives you EH. And so that allows you to add DEH. So DEH gets added. So what are we doing? So what we're doing is we're trying to, in order for a compatible to be grown to a larger compatible, it must be the case that D is compatible with E, D is compatible with H, and E is compatible with H. So they're all mutually compatible with each other. So we've done that by showing that E and H are compatible, or sorry, that E and H are compatible here, and then D is compatible with E, and D is compatible with H. So that those three implications together allow us to add DEH into this entry. So then I move over to column C. So, and then we remove any duplicated entries at this point. And EH is a subset of DEH, so I can remove EH. It's redundant now because it's a subset. It's not a maximal compatible because it's a subset of a larger compatible. So now I can move on to column C. So what are going to be, Vikas, what are going to be the entries I put here after C?
DFG.
DFG, exactly, DFG. And if I intersect DFG with FG, what do I get?
FG.
FG. So that means I get to add CFG to my list.
Yes.
If I intersect DFG to DEH, what do I get?
D.
Just D, which means I get to add CD to my list. So I'm adding CFG, which I replace FG because it's redundant now, and because this is larger than that set. And I added CD to my list. Okay. So Meher, what goes in B?
B is BE and BD.
B is, sorry, what after B goes, what are the three letters that are going to go after B?
Oh, wouldn't it just be, wait, I'm confused.
So it's the entries that could potentially be compatible with B. I'm on column B now. Another way of looking at it, the entries without an X.
Yeah, so wouldn't that be just B and E? So E and then.
So what are the rows that don't have an X in this column?
That's C, D, and E.
So it's C, D, and E.
Oh, I see. Okay.
You got it? Okay. Now, if you take C, D, and E and you intersect that with CFG, what do you get?
C.
C. So we get to add BC to the list. If we take CDE and we intersect it with DEH, what do you get?
D and E.
D and E. So we get to add BDE to the list. If we intersect CDE with CD, what do you get?
CD.
So what do you get to add to the list?
CDE.
Nope.
Just E.
So I intersect CDE with CD, you get CD. And then you get to add you get to add the intersection plus the column you're working on.
So CDB.
BCD, yeah. So after removing subsets, I've got CFG, DEH, BCD, and BDE now. So you can see that they keep growing as we go down. And then Ji-Chen, how about column A?
BDE.
BDE and?
BDE and G.
G. Oops. Shoot. B, D, E, and G. There's the whole solution. I should have animated that twice. Okay, so you added B, D, E, and G, and then you see B, D, E, and G. It intersects with B, D, E, which means that you should be able to add A, B, D, E, which it did. And then G, CFG, B, D, E, G intersects with CFG, and just with G, and you get to add AG to the list. And that is the end. So our maximal compatibles are CFG, DEH, BCD, ABDE, and AG. So these are groupings of states that could be merged together. So I could go back to my initial thing and see, for example, way back here, right? So C, F, and G could all potentially be merged together. C, F, and G, for example. Now, I'd also have to merge D and C to make that work out, and I'd also have to merge H and E, but there's no problem potentially with merging those, assuming I can merge the other parts. So what this output is telling you is that these are groups of states that could be merged all at once into one grouping. Basically, I can merge 3 rows to form one new row in my reduced table. Or I can merge these 3, or I can merge these 3, or these 4, or these 2, or any combinations of these, as long as every single state is covered at least once. Does that make sense? So every row, you need to keep every row in the end, but you can merge them in with other rows to get a smaller table. Now, there's one other technique for doing maximals, which is somewhat simpler, or different. I don't know, simpler. I mean, it might be more computationally intense. So another way of finding maximals is if you take for each Si and Sj, which are incompatible, we know that no maximal compatible will include both of them. So we can write a Boolean formula that gives the conditions for a set of states to be compatible, where for each state Si, Xi equals 1 means that Si is in the set. And then for every incompatible pair, you add a clause of Xi or not Xj is included. And this forms a conjunction of clauses for each incompatible pair. So for this particular table, we get this clause because A and C are incompatible. That means A and C can't both be included in any compatible. So either the compatible does not include A or it does not include C because it can't have both A and C in it. Similarly, A and F have an X in it. They can't both be included, etc. For every X, you put in one of these pairs. Then what you do, you take this product of sums and you multiply it out. So you just do your sort of method where you multiply this out to form a sum of products. And you remove any subsets. So this sum of products indicates in reverse all of the compatibles. So a compatible that does not include A, does not include B, does not include D, does not include E, does not include H. Well, that's the same as saying it does include C, it does include F, it does include G. So each one of these clauses represents the complement of a maximal compatible. Anything not listed is a member of the maximal compatible set. So this approach, I mean, this is simpler. There's a lot less rules to it, right? You basically form your clause and then you multiply it out. But can anyone think about why this might not be a smooth approach? If I multiply out a formula like this, how many of terms are you going to get when you multiply out?
Yeah, memory would be much high to convert to sum of products.
Yeah, when you convert from product of sums to sum of products, you could end up with a lot of terms. It actually is exponentially related to the size of the original formula. So converting between sum of products to product of sums or product of sums, sum of products can explode your representation. And so in general, you can get a lot of terms. And some of them are temporary because you're going to remove them because they're subsets of others. But it still could be very memory intensive. Okay. So I'm just going to mention the next part, and then we'll talk about it on the next time, which is prime compatible. So when we calculated maximal compatibles, we didn't worry about the other mergers that had to be merged. So like when I came up with a solution that said CFG could be merged, Well, C, F, G, if they're merged, you also need to merge C and D. So if I pick C, F, G, I have to pick something like D, E, H that merges, I have to pick something like B, C, D that also merges C and D. And if I pick D, E, H, well, D, E, H, they're all mutually compatible, so that's not a problem. B, C, D, B, C, B, D. If I pick B, D, B, C, D, I need to merge A and B, for example. So I need to find something that merges A and B. So I'd have to pick, for example, that merger. So you have this, this is what makes this going to be a binite covering problem, because if I pick one compatible, I might have to pick another one so that the next states will line up. And it also turns out that because of this implication, it might be the case your solution might not just be composed of maximals. It might be the case that merging too many things gives you too hard a problem to solve with merge other things. So what I'll introduce next time is a technique called prime compatibles, which are basically maximal compatibles that have less requirements on them of other things that have to be merged. And so that's what I'm going to pick up with next time. And so the plan is that next Tuesday at the regular time, I'm going to go through the last little bit about state minimization. And then on Thursday, Ken Stevens will come to your class and lecture on state assignment next week. So, I'm hoping actually if you guys can possibly meet like at 9 instead of 9:10 on Tuesday. Is that okay?
Yeah.
And how was this? Did this work out?
Yeah.
All right.